Come back. How are you finding the problems? Are you able to solve on your own? If you're able to solve on your own, then I think you're ready for the examination. I think test 1, the problems are over. Now let us start test 2 problems. Okay. Problem number 1. Match the following. Cascode amplifier, option B, differential amplifier, C, Darlington pair, which is CC amplifier configurations. Okay. Number 1, does not provide current gain. It's like no current gain. Number 2, wideband amplifier. And number 3, low input impedance, RI is low, high current gain, A is high. Number 4, high input impedance, high current gain. Number 5, high common mode voltage rejection. High common mode voltage rejection, which is nothing but common mode gain is 0 or close to 0, very small. Therefore, tell me what is the answer? A, cascode amplifier. Cascode amplifier is nothing but wideband amplifier. And differential amplifier, your common mode signals will not be amplified. That will be almost 0. Darlington pair, your input impedance is high and current gain is also high. Okay, that is what is the answer. Therefore, what is the answer? A is 2, your A is 2, your B is 5, your C is 4. That is the answer. Okay. Why cascode amplifier is wideband amplifier? I told you, right, the gain is improved without affecting your unity gain bandwidth. But if you take your cascade amplifier, your gain is improved by affecting your unity gain frequency or by affecting your bandwidth part. Okay. But in the case of cascode, without affecting your unity gain frequency, your gain will be improved. That is why it is called as wideband amplifier with respect to cascade amplifier. The wideband is with respect to cascade bandwidth. Differential amplifier, we know that it will reject the noise signals or common mode signals. Therefore, high common mode voltage rejection or common mode gain is 0. There is no gain means it is not amplifying the common mode signals. And Darlington pair, we know that CC amplifier. CC amplifier is having very high input impedance and the current gain is more. And then we solved one problem, the Darlington composite transistor, the current overall HFE we calculated, we got around 10,000. Okay, that's fine. Now let's see problem number 2. What is problem number 2? In the differential amplifier of the figure, if the source resistance of the current source IEE is infinity, then the common mode gain. Okay, what is your common mode gain? Actually, the circuit is Let us say this is V1, V2, right? And this is what is your V01 and V02. What is common mode gain? I think I already explained. When you short, our V1 is equal to V2. Therefore, physically, if you ask me, when you short, V1 is equal to V2, and then if you say that is what your V common mode, then V01, V02, then your common mode gain is defined as for the same signal, and if you vary this, right, then what is the change in V01? What is the change in the V01 due to the change in common mode voltage? What is common mode voltage? V1 is equal to V2 is equal to VCM, let us say, or V1 plus V2 by 2, or your VCM is equal to V1 plus V2 by 2. Okay, therefore, or the change in V01 with respect to common mode voltage change, and the change in V02 because of common mode voltage change. When both are shorted and then varies, then what is the change in V01 or what is the change in V02? I am expecting change in V01 with respect to common mode signal variation. The signal which is common for both V1 and V2, that should not impact your V01 and V02. That we don't want. But the differential voltage V1 minus V2, that should be amplified. But I don't want to see any common mode signal amplification. Example, noise. The noise is common for both V1 and V2. I don't want to amplify. That should be rejected. Therefore, ideally I want this to be 0. Therefore, this is what is 0 ideally. But practically if you take, let us say if this is what is practical current source having some resistance Re, internal resistance, then your common mode gain we got, if you take mod ACM magnitude only, you will get RC divided by 2 Re. If Re is infinity, then what is your common mode gain? Your common mode gain will be 0. Therefore, what is the answer? Answer is A. Answer is A. Take it. If the bottom current source or tail current source is ideal, then common mode gain will be 0. That is what we need. That will reject perfectly the common mode signals. Done? Okay. Problem number 3. Introducing a resistor in the emitter of a common emitter amplifier stabilizes the DC operating point against the variations. Okay. If you take CE amplifier, it's fixed bias circuit or what it may be. This is what your RC, the bias value RB, and this is what your VCC. Okay, without any combination. Right? Then this is what your input. If you take DC circuit, There is no Q point stability. No Q point stability. We have seen, right? Why? We know that IC is equal to beta into IB plus 1 plus beta into IC naught. Therefore, your IC is function of reverse saturation current, base current and beta. In turn, all are depending on temperature. Therefore, if temperature changes, IC changes, Q point. Therefore, Q point is not having any stability. But when you introduce what you call RE, that is nothing but your self-bias circuit in DC or CE with RE amplifier in AC. CE with RE amplifier. But is speaking about Q point stability, therefore we need to consider only DC circuit. Therefore, this is what is speaking. And this is what you have. And this is your VCC, RC, RB. Now this is what your RE. Now because of this, whatever current, right? Then your Q point is stable. Point is stable. And we got stability factor. S is equal to 1 plus beta into RB plus RE divided by RB plus 1 plus beta into RE. If you neglect this RB part, then it is approximately 1 plus RB by RE. If you increase RE, your stability will increase, right? As RE increases, the negative feedback increases. Negative feedback. Why negative feedback increases? I will tell you. See, as RE is increasing, whatever current you have, this is nothing but DC current, right? Whatever current you have here, this is your collector current, DC collector current, this is IC. The same thing is almost flowing through your RE, right? Then, if RE is increasing, for the same change in IC, more voltage, more VBE means more feedback to input, more decrement in VBE, more decrement in IB, more control of IC. That is what is having maximum negative feedback. Okay, your negative feedback increases, then your stability factor is also will be improved. I want stability factor to be equal to decreasing, then stability increases basically. Okay, that's fine. Therefore, what is the answer? Due to temperature or due to any reason, if IE is increasing or IC is increasing or Q point is changing, RE will come into picture, will make it stabilized. Therefore, what is the answer? Answer is temperature as well as beta. Not only temperature, even the beta is changing. In turn, the temperature is also affecting beta. Therefore, indirectly, or if you replace the transistor, also it will control. Okay. Therefore, answer is C. Answer is C. It will control both. Okay. Now, problem number 4. It is also qualitative problem. If you see, the current gain of a bipolar transistor drops at high frequency because of at high frequency, whether it is current gain or voltage gain. Remember, it follows what? It follows your band pass filter. Therefore, at high frequency due to internal caps, BJT, internal caps, internal parasitic capacitance. Therefore, what is the answer? Transistor capacitances, high current effects in the base, no. Parasitic inductive effects, no. Early effect, no. Answer is A. We had seen this, right? Fine, take it. Then after that we will see problem number 5. 30 seconds more. After that we'll see problem number 5. Done? Okay. Circuit is given. (430 ohm) RC, 10 kilo ohm, 5 kilo ohm, then this is your IC and 15 volt. Okay. VBE is 0.7 volt. This is also given, and beta is very large. When beta is very large, you can neglect IB with respect to IC. Then what is asking is, what is IC? Now observe, this is AC analysis or DC analysis? It is DC analysis problem. Then beta is very large. What do you mean by beta is very large? Your IE, this is nothing but your IE, right? This is your IE. Therefore IE is equal to IC plus IB. Therefore IC plus IC by beta. If beta is very large, this value is almost 0, then IE is nothing but IC. That is the meaning of it. You can neglect IB with respect to IE. That is the meaning of beta very high. Therefore your IE is approximately equal to IC. If you find IE, indirectly you are finding IC only. Okay. Now can I apply Thevenin's theorem? This is nothing but a self-biased circuit, right? If you apply Thevenin's theorem, this is nothing but your V Thevenin and then R Thevenin. This is your V Thevenin and this is R Thevenin. Okay, and this is your RC and this is 15 volt and now 430 ohm and this is your IE. Okay, and this is what your IB. And what is your V Thevenin? Your V Thevenin is equal to what? R2 divided by 5K divided by 10K plus 5K. 15K potential divider network into 15. KK will be cancelled. This is nothing but 5 volt. Okay, what is our V Thevenin? V Thevenin is 5 volt. Then apply loop KVL. What is R Thevenin? 10K in parallel to 5K. What is your R Thevenin? 10K in parallel to 5K. Now, if you apply input KVL, loop KVL, input KVL, V Thevenin is equal to IB into R Thevenin plus the VBE plus the drop across this IE into 430 ohm. This voltage is equal to this voltage plus this voltage plus this voltage, or if you do minus V Thevenin plus this is equal to 0, both will give you the same value. Now with respect to IE, can you neglect IB? That's what he told, right? You can neglect IB, therefore it is approximately equal to 0. Then what is your IE? Therefore this is nothing but 5 is equal to 0.7 plus IE divided by 430. Therefore what is your IE? IE is equal to 5 minus 0.7 divided by 430, which is 4.3 divided by 430. Then 4.3 1 by 100, 0.01, which is 10 milliampere. Therefore what is your IC? IC is approximately equal to IE, therefore it is 10 milliampere. What is the answer? Your answer is D. Answer is D. I'll give you 1 minute time. Try to solve it on your own. Then we'll see problem number 6. Done, right? Now problem number 6. Three identical RC coupled transistor amplifiers are cascaded. If each of the amplifiers has a frequency response as shown in figure, the overall frequency response is given by. Okay. Given there are three RC coupled amplifiers, they are in cascaded. They are in cascade configuration. Then he is asking what is overall transfer function. If this is what is having something like this, which is what is given, then what is our overall? Okay, and it is also given what is that. This is what is, if I zoom this is nothing but your 20 Hz, and this is what is 1 kilohertz, and this is what is 0, and wherever you are seeing minus 3 dB. This is what is mod AV in dB. Okay, this is what is given, and then what is overall transfer function? See, we know that this is what is single stage. This is single stage frequency response. Now, if you take multi-stage, the frequency response will be, if you take single stage frequency response like this, the multi-stage frequency response will be, your gain will be improved, but your bandwidth will decrease. Therefore, this is what is our 20 Hz, then this is what is your okay, and this is what is your 1 kilohertz, right? Then three stages if you take mod AV dB, what will be the newer cutoff frequency? That is what is asking. What is the frequency response of RC coupled amplifier? Now if you see, this is what it is and this is what it is. Okay. Now this is what your 3 dB. This is what is our 3 dB. Here also this is what is your 3 dB. This is your 3 dB, minus 3 dB. That is the step. That is why it is 3 dB cutoff frequencies. This is also minus 3 dB. Now what is this? This is nothing but your new lower cutoff frequency, let us say FL star, and this is new higher cutoff frequency FH star. And I gave you formula. What is FL star? FL star is increasing. Therefore, that is nothing but your FL divided by 2 to the power of 1 by n minus 1. Similarly, what is your FH star? That is decreasing, right? Then FH into 2 to the power of 1 by n minus 1, where n is nothing but where N is equal to 3. If you substitute, what is FL star? Your FL star is equal to FL divided by 2 to the power of 1 by 3. 2 to the power of 1 divided by 3 minus 1. What is this value? What is 2 to the power of 1 by 3? It is approximately 0.5. Therefore, this is nothing but, means when you do this, this is nothing but 1 by 2. Therefore, FL divided by approximately 1 by 2. Therefore, it is nothing but 40 Hz. Similarly, what is your FH star? Your FH star is FH into 2 to the power of 1 by 3 minus 1. 1 by 3 minus 1. Again, this is nothing but FH by 2, because FH into 1 by 2. Therefore, which is nothing but 0.5 kilohertz. Therefore, what is the answer? Your FL star is 40 Hz and your FH star is 0.5 kilohertz. What is the option which is satisfying this? 40 and then 0.5. Answer is A. Answer is A. Your bandwidth will decrease. Very simple. Almost 1 kHz bandwidth became 0.5 kHz bandwidth. Because your gain is improved, your bandwidth will decrease. That is expected. Okay. Take it. After that, we will solve problem number 7. Done? Okay. Problem number 7. Choose the correct match. Choose the correct match for input resistance of various amplifier configuration shown below. Common base, common collector, common emitter. I think directly we can say, if you take common emitter, what is your RI? For common emitter, your RI is moderate. That is what we have seen. If you take common collector, what is your input impedance? Because this is voltage amplifier, it is high. And if you take common base, it is a current amplifier. What is your input impedance? Low. Right? Now using this you can get it. Okay. So tell me, what is the answer? First of all, common base low, correct? Common collector, wrong. Option A is not correct. Common base, no. Either C. Common base, low, yes. CC, high, yes. CE, moderate. Therefore, what is the answer? Answer is C. Now, problem number 8. Done, right? Answer is C. Problem number 8. For the BJT Q1 in the circuit shown below, beta is infinity. Infinity in the sense very high. VBE on is 0.7 volt. VCE sat 0.7 volt. Actually, typically VCE sat is 0.2, but it is saying the problem is saying that it is 0.7. Fine. The switch is initially closed. At a time t is equal to 0, the switch is opened. The time t at which Q leaves the active region. This is interesting problem. Okay. Let's see problem number 8. The problem is, this is the circuit which is 0.5 milliampere and minus 10 volt, minus 5 volt. Don't say base is minus 5 therefore off. No, this is minus 10. This is important. And this is 4.3 kilo ohm. And now this is what is having a switch. Okay. And then switch is open at time t is equal to 0. Till then there is a capacitor which is 5 microfarad. Okay. Therefore the switch is opened at a time t is equal to 0. Okay. Now what is saying VBE on is equal to 0.7, VCE sat is equal to 0.7. What is saying that switch is closed. Initially switch is closed. At a time t is equal to 0, switch is opened. At a time t is equal to 0, switch is opened. Whenever you are opening the switch, that is what is time t is equal to 0. Then the time t at which Q1 leaves the active region. The time t transistor Q1 or Q leaves active region from t is equal to 0. Means the moment when you open the switch, it will take some time. After some time, it will come out of active region and entering into some other region. Therefore, indirectly it is saying that before closing the switch, or it is in active region, then it is coming out of active region. That is what he is saying. Okay. Now, see how to analyze these type of problems. Simple. Now, first of all, just to understand the KCL, KVL and all those things. Okay. Now, let's have t less than 0 where switch is closed. Only at a time t is equal to 0, switch is opened, right? Therefore, when switch is closed, let's analyze the circuit. That should be in active region. That is what according to the problem. Okay. If that is the case, let's see what is the circuit. T less than 0. Therefore, this is what your transistor minus 10 minus 5 and this is 4.3K. Now, this is what is connected. Therefore, it is connected to ground. Then even though you have capacitor, doesn't matter. Therefore, now what is the voltage across the capacitor? 0, because capacitor in parallel to a short circuit, 0 only. Okay, that's fine. Therefore, this is also 0. This is 0.5 milliampere and this is what is your 5 volt. Okay. Now, let's analyze or let's get. Therefore, now this is also 0 volt because this is 0. This is nothing but 0. This is also 0 volt. This is nothing but your collector. This is your base. This is your emitter. Okay. Now, let's try to see what is the collector current. Therefore, let's see what is the collector current. Okay. Let's see what is IC. The same current is almost flowing through IE. Therefore, let us say this is what is your IE. And he told that beta is very high. He told that beta is very high. Infinity means beta is very high. Then you can neglect IB, then IE is equal to IC. That is the meaning of it. Okay. Then can you write input loop KVL? If you write input KVL, then therefore to find IE, input KVL. What is the voltage drop between these two nodes? Minus 5 minus of minus 10. Minus 5 minus of minus 10 is equal to, this voltage is equal to VBE plus the drop across this, which is nothing but IE into 4.3 kilo ohm. Minus 5 minus of minus 10. 5 is equal to VBE 0.7 plus IE into 4.3 K. Then IE is nothing but 5 minus 0.7, 4.3 divided by 4.3 K, 4.3, this is nothing but 1 milliampere. Therefore, what is your IE? IE is nothing but 1 milliampere. What does that mean? Therefore, you see, this is 1 milliampere, this is 1 milliampere, your IC is also 1 milliampere. Now let's satisfy, KVL is done, now let's satisfy output side. Tell me what is the current is entering into your transistor? 1 milliampere. But we know that this current source is giving only 0.5 milliampere. Then where is that extra 0.5 milliampere is coming? This is giving only 0.5 milliampere, but it is asking 1 milliampere. Then that extra 0.5 milliampere is coming from this branch. Means basically coming from this. This is what is our 0.5 milliampere from ground. You can say how the ground is giving current. Remember, to satisfy KCL, KVL, ground can give you current, ground can take current. But remember, ultimately KCL and KVL will be satisfied. But I can explain in a different way. Ground is giving current means somewhere, someplace, it is taking current. Ground is taking current at a different node. I'll explain. Where is that? Tell me, this is what is minus 1 milliampere, right? That minus 1 milliampere is entering into minus 10 of battery plus it is connected to ground. Therefore, indirectly through battery, 1 milliampere of current is going through ground. Out of that 1 milliampere of current which is going to ground, this is 5 volt to ground, 0.5 milliampere is coming from this ground through battery of 5 and then entering into this. Again another 0.5 is coming from this ground. Therefore 1 milliampere is entering into ground, 0.5 and then 0.5. Again two different ground, it is giving 1 milliampere. Satisfied. Fine. Now let's see what is VCE. IE is done. Now let's see output KVL. When you do output KVL, right, output KVL, this is nothing but 0, 0 minus of minus 10, 0 minus of minus 10, that is nothing but voltage between collector to this node is equal to VCE plus IE into 4.3 K, which you already know. Therefore this is 10 is equal to VCE plus 4.3. Therefore what is your VCE? Your VCE is equal to 5.7 volt. Your VCE is 5.7 volt. Therefore, which is greater than VCE sat in this case 0.7. It is greater than VCE sat, which is 0.7. Therefore, it is in active region. It is satisfied. Therefore, indirectly, if switch is closed, the transistor is in active region. If switch is closed, transistor is in active region. Now the problem is, I see, we are not solving the problem, I am explaining the problem. When switch is closed, 1 milliampere of current is flowing through the transistor. Out of that 1 milliampere, 0.5 is coming from this current source, remaining 0.5 is coming from this ground. Okay, then VCE is equal to 5.7, which is greater than 0.7. Now what he is saying is, at a time t is equal to 0 or t greater than or equal to 0, your switch is opened. Switch is opened. Okay, then it is like this is what your current source. Remember, if BJT is in active region, that is also current source. Okay, maybe equivalently, maybe if you ask me, equivalently, this is nothing but a current source which is 0.5 milliampere, and now your BJT is also current control current source that is taking 1 milliampere, but it is connected to a ground. Therefore, to satisfy KCL, this is 0.5 and then extra 0.5 is coming from this. This is what we have, right? Basically, this is what is your 5 volt. This is nothing but your current control current source. Okay. Therefore, what it will be? That is what we calculated. Now, what is our circuit when T greater than or equal switch is opened? When switch is opened, this is what is your 0.5 milliampere. This is the transistor, minus 10 volt, minus 5 volt. When switch is opened, only capacitor is there now. But initially, what is voltage across the capacitor? Voltage across the capacitor is 0 at a time t is equal to 0. Because earlier it was short circuit to then it is 0 at time t is equal to 0 only. Now this switch is opened. There is no path to ground. Therefore now this is 5 volt. Okay. Now this is 4.3K and the current which is what is flowing through this is nothing but 1 milliampere. Therefore here this is also 1 milliampere, but this is giving only 0.5 milliampere. Then remember, still it is a current source only because it is in active region. If it is in active region, it is a current source only. But remember, one switch is not there. From where you are getting that extra 0.5 milliampere? Earlier ground was giving that current. The ground was giving current. Now there is no ground because your ground is disconnected. Now capacitor is there. Therefore there is a ground here. Therefore that current is coming from this ground. But indirectly current is flowing through the capacitor. When current is flowing through the capacitor, it is equivalent to the 0 volt what you have, the capacitor, that is discharging. Then only this is what is giving current, but with constant current. Okay. Therefore, that extra current has to come from the current. It has to come from your capacitor, actually from the ground, but the current is flowing through the capacitor. If constant current is flowing through the capacitor, right? If current is entering into capacitor, your capacitor voltage will increase. Because current is leaving from the capacitor from network analysis, your voltage will decrease from 0, 0, minus 1, minus 2, minus 3, minus 4 like that. Therefore, it is discharging. Now, the point is, yes, the moment when you open the switch at a time t is equal to 0, how much time it will take such that it will come out of active region? That is what he is saying. When it will come out of active region and what is the condition to check whether it is an active region or not? That is nothing but your VCE. If VCE is greater than or equal to VCE sat, then active region, else saturation region. What are we? Let's see. Therefore, now tell me what is your collector voltage. Now you don't say your collector voltage, whatever you are saying is 0. Earlier it is connected to ground, therefore it is 0. Now that is nothing but voltage across the capacitor, right? Now this is nothing but voltage at the emitter, right? Then we know already this point, right? Therefore now when this voltage, because what is voltage at emitter? Voltage at emitter is equal to 4.3 minus 7, that is nothing but minus 5.7. That is voltage at emitter. Now what is voltage at collector? Your voltage at collector is equal to 0 at a time t is equal to 0. Tell me, for voltage at collector is equal to minus 5 or less than or equal to minus 5, then your VCE will be what? VC minus 5 minus of minus 5.7, then it will be less than or equal to 0.7 volt. Then it is entering into your Q, will enter into Q leaves active region. This is what is very important point. If you understand this, problem is over. If voltage across the collector or not capacitor, I think both are same only. This is nothing but VC with respect to ground. Okay. If VC, see, but remember this is what is your at a time t is equal to 0. Therefore, these are all at a time t is equal to 0. But this is what is minus 5.7, time t is equal to 0. Okay. Therefore, now when VC is less than or equal to minus 5, then your VCE, your voltage at emitter is not changing because this is 1 milliampere only. Then it will be less than or equal to 0.7. Then your Q leaves active region. For what time when the capacitor current is flowing through, the current which is flowing through the capacitor is 0.5 milliampere, then for what time the voltage across the capacitor will be equal to minus 5, that is the time where the transistor will come out of the active region. If you calculate that, then problem is over. Okay. Therefore, if I calculate, you will get the answer. Therefore, what is that? We know that voltage across the capacitor is 1 by C integral I into dt. If I is constant, 1 by C integral I into dt, then you will get I by C into T. Let me take mod Vc. Mod Vc should be equal to -5. Then your mod Vc should be, then you will get positive, current negative. Instead of having all those things, the time T is equal to Vc into C divided by I. Therefore, your time T is equal to mod Vc into C divided by mod I. If current is entering into capacitor, positive. If current is leaving from the capacitor, negative. Anything is fine. Therefore, mod Vc is nothing but 5 into, what is C? 5 microfarad. What is current? 0.5 milliampere. Therefore, micro, kilo, milli is 50 millisecond. If you calculate, you will get 50 millisecond. Therefore, the moment you open the switch, within 50 millisecond, this voltage will go from 0 to -5. Then VCE will be, your VCE will be less than or equal to VCE sat. Then it will enter into saturation region. It leaves active region. Okay, that is the problem. Okay, fine. Therefore, this is also a current source. Therefore, indirectly, if you ask me, I can represent it like this. This is a current source. This is a current source. Okay. Now, this is asking 0.5 milliampere. This is asking 1 milliampere. But there is a path which is nothing but your capacitor. Now, that extra current has to come from the capacitor only. That is nothing but your 0.5 milliampere. Therefore, your capacitor voltage will decrease. The voltage across the capacitor will decrease. Your VC decreases. That is what it is. Okay, that's fine. To satisfy KCL. Take it. I'll give you 1 minute time. Then we'll see next problem. This is problem number 8, right? This took a little bit more time, but that's fine. If you understand the concept, then that is fine. Done, right? Okay. Problem number 9. The output voltage of a regulated power supply shown in figure. This is straightforward. Circuit is, this is what is given. Circuit is bigger, but solution is faster. 15 volt DC unregulated power source. Unregulated power source. It is op-amp problem, okay? Then this is what is having 1 kilo ohm and a GA diode, and this is what is given to op-amp plus minus. Then it has a resistor, and this is what is given to a transistor, and this is what is the output, okay? Okay, fine. This is This is what is your 40 kilo ohm and this is 20 kilo ohm. This is what is your regulated DC output. This is what is your regulated output. Regulated DC output. And VZ, the GR voltage is 3, this is reference voltage and this is what is your 1 kilo ohm. Now asking for what is your V0. Okay, what is V0? We know that this is a regulator and it is an op-amp problem. Surely op-amp should be, if you want to control anything, op-amp should be negative feedback. If you want, you can control that also. Okay, you can find that also. How will you find? Open the loop, increase the voltage, increase this voltage, then come back. You see, you'll get it. Therefore, it is a negative feedback. If op-amp is a negative feedback, then can I apply virtual current concept? Yes, right? Therefore, tell me what is the voltage at this point, because this is what your 3 volt GNR diode having a 3 volt battery. This is your reference, this is 3 volt. And now this is nothing but your V0. When you say this is what your V0 and this is what your beta network, right? This is R2 and this is R1. Let us say this is your R1 and this is your R2. Then what is this voltage? This is nothing but your beta into V0. Therefore, what is if op-amp is a negative feedback, then virtual current concept is valid. Then what is your beta V0? Beta V0 is equal to 3 volt. Therefore, beta into V0 is equal to 3 volt. What is beta? R2 divided by the sampling factor from V0. R1 plus R2 into V0 is equal to 3. What is R2? 20k divided by 20k plus 40k, 60k into V0 is equal to 3. Then kk will be cancelled. It is 1 by 3. V0 by 3 is equal to 3. Then V0 is equal to 9 volt. Therefore, what is your output voltage? 9. For what is the answer? Your answer is C. Very simple, right? The problem is virtual current, the understanding. Therefore, virtual current concept is valid. Then whatever voltage you have, the same voltage is expected here. But what is this voltage? If I say V0, part of that is sampled. R2 divided by R1 plus R2 into V0 is that. That is what we are applying to inverting terminal. That is nothing but that is trying to track to your reference voltage. That is 3. Therefore, to track that, what is V0? V0 is 9 volt. That is what we got it. Okay. Take it. Time is over for this session. Then we'll continue in the next session for remaining problems. Okay. We'll continue in the next session. Thank you.